like I said, there's some optional topics I wanted to do from 2.9, just a couple differential equations I wanted you to know how to solve. There are a set of equations called Bernoulli equations. They have the form equations which, as you may recall, the last homework problem in 2.9, after we did that substitution, we actually ended up with something like this. There was a V2 down this side, right? It was a Bernoulli equation. I expected to have told you this about it before that homework, but we never got around to it. Tell me what happens if n is 0. What kind of equation is this?
No, it's linear.
It's linear. Right? So we know how to deal with that already. What if n is 1?
No, we're not.
It is still linear. Right? And it's even separable in that case. Alright. But if n greater than 2, then the trick to do this is to do a substitution of v equals y to the 1 minus n. Right? This gives so example. So it's a first order nonlinear equation. It's not linear because of this, and it's also not separable because of that. But I can write it in the form equals, and that means it's actually a Bernoulli equation. And so what we can do is set v equals this, right? But here your n is 3. Now, if v is actually y to the minus 2, right? What would your y prime end up being? I took v prime, this would be minus 2y to the minus 3.
That's my fault, I'm sorry. This is good.
Yeah, okay. So what do you think we need to do here? We want to start to swapping things out, right? So what do we need?
Multiply by the multiply.
We need y prime.
We need y prime. How do we get to y prime?
We divide both sides with -2 and 2
Divide both sides by -2?
to get the -2 on the other side.
Integrate what?
Integrate with y, or integrate the v with respect to y.
Integrate the v with respect to y.
No, just probably replace v and v prime to the equation.
I want t as the independent variable here. The other one is, I want to keep t as the independent variable. There's another technique for another thing where we actually want to switch it to y. But How do we do that?
Partial derivative. With respect to t. Take y with respect to t.
Differentiate with respect to t. So what would that give us here?
0.
You get 2 y to negative 1.
I have v equals y to the minus 2. How do I...
V minus 2y negative 1 dv dt.
Come again? What did you say?
It'd be negative 2y to the negative 1 dv dt times dv dt. Or dy dt.
Y to the minus 1. Y to the minus 1.
I mean, minus 3.
So we're differentiating with respect to t, right? So we have minus 2y to the minus 1 y prime, right? Can we actually do that?
Isn't this supposed to be
Minus
y to the negative 3?
Yeah, minus 3, yeah.
But, you said minus 1. Okay. Okay, so this means then that I can actually solve for this y prime, right? And y prime would be what here? Just move those guys over, right? So I can multiply by y cubed, and I can divide by minus 2, right? And then now I can start to plug these guys into my differential equation. Y prime, I will replace with this guy, v prime y cubed over minus 2, plus let's leave this guy for a second, because we're gonna see what's gonna happen. Now what you can do is you can divide both sides by y cubed, right? So I divide this by y cubed, I just get v prime over minus 2. Divide this by y cubed, I get y to the minus 2. Divide this by y cubed, I get 1 over t squared. What is this guy? That's actually just v. This means I can multiply by 2. And I multiply both sides by minus 2. And notice what we have here is a linear equation in v. Right? We have v prime plus p of t times v equals some g of t. And so we know how to solve that, right? Find the integrating factor. Equals e to the minus 4 ln t equals t to the minus 4. So t to the minus 4 times v all prime is equal to, this here is t to the minus 2, multiplied by t to the minus 4, get t to the minus 6. This means that t to the minus 4v is equal to the antiderivative of this, which means I add 1 to the power, divide by the new power. This means that your v now is 2 over 5 t to the minus 1. And so this means I solve that for v. So how do I get to y?
Replace.
Right, v is just y to the minus 2.
Over 1 square.
Constant of integration here, which means here I have c over, well, c t to the 4th. And so this guy is equal to 1 over, I was taking a square root, let's leave this as a square. I'm giving an initial condition where if the initial condition gives me a positive output, I can take the square of both sides, take the +1 or the -1. I think it's nicer to leave it like that. So this kind of differential equation is called the Bernoulli differential equation. Once you can write it in this form, where your n is bigger than 1. N is an integer.
Plus another question.
Yes.
If let's say I'm given a negative initial condition, do I put a square root and then put negative sign outside? Square root?
Yeah, because you'd have to take the square root of both sides, which gives you plus or minus, and you choose which one matches the initial condition. What else did I want to show? So Bernoulli equations actually show up all the time. You probably won't see it on a final, but it's a good thing to know. It should pop up in your other classes at some point. These are 2 lines if I should even do this. Form is if we have something like y double prime equals f of y and y prime, meaning there's no t, there's no independent variable. So the trick here by the chain rule we would get dv dt is equal to dv dy times dy dt. This is equal to dv dy times this guy symbols v. So these are, you have to do it sort of strangely. You don't want to think of t as the independent variable anymore. You sort of do this swap and you think of y as the independent variable, right? So I'm looking at things as derivatives with respect to y. So here is y. Or we'll do the other example. Or I'll ask you guys to do it on your own. Actually, I have a lot to get through in chapter 3. Okay, so here, there's a differential equation. Clearly, it's nonlinear. I have 2 y's multiplying each other, and here I have a y squared, but there is no t. Right? The independent variable is missing. We can still solve this guy. So just follow this. Set v equals y prime. This means you can have dv dt equals dv dy times v. This implies you can just start plugging this in. By the way, if v is y prime, dv dt is actually y double prime. Right? Forgot to mention that. Right, I just took the derivative. Okay, so now I can start to plug these guys in. And so here, I have, instead of y double prime, I have dv dy times v. Y prime is v squared. There's a y left over, but now we're sort of thinking of it as the t, right? It's the independent variable now. And so How do we, yes,
You'd have to divide y from both sides, so you'd have dv dy v plus v squared over y equals 0, make it a linear ODE.
it won't be linear, the v
What's
is
the
squared.
square?
Okay.
So it still won't be linear.
Divide by the
Exact.
You think it's exact? That's thinking too hard.
This is rough. You think hard. Supposed to think hard. Your brain starts to pop. I don't know. Yeah, divide by v.
You could divide by v, but what does that make it into?
Uh,
Now it's separable. I can, it's minus 1 over y over v times v. Alright, I just move this over, you get minus v, divide by y, and then I divide the v back over here, move the y prime. This point, integrate both sides, this means that ln of v is equal to minus ln of y constant. This implies b is equal to c over y. This implies y prime is equal to c over y. How do we solve that one? There's a y on this side. We're back to y prime, right? Now remember, y is a function of what?
no?
T.
dt. God damn it.
Right, so there's a y over here, I can't do that. Right, you have to keep track of who's the independent variable here. This one you actually switched for a while, but now we're back. So what kind of equation is this? It's separable again, right? This is really dy dt is equal to c over y. Which means I can say y dy is equal to c dt. Integrate both sides. This is y squared over 2 is equal to ct plus another constant. This means that y squared is equal to ct plus constant. Then I multiply them by 2, but they're still just arbitrary. That would be nice for you guys to see things like that. Try. So we can move on. Y double prime plus y prime squared equals 2e to the minus y. Let me see how you guys do on that. Try that on your own. If I'm bored, I might put it as a bonus problem on a test or something. I don't know. But really, there are way more kinds of first-order differential equations than we've shown you, and way more techniques. But for our syllabus, really, everything we've done in Chapter 2 before is all you're really responsible for. But I thought it was good for you guys to see some of the other techniques out there. And you better jump into Chapter 3 because it's actually a lot of writing. There's one technique that's done in 3.1, but I think a lot of background is necessary to really understand what's going on. So we're going to start Chapter 3, which talks about the second-order linear equation. In section 3.1, we focus on the homogeneous equations with let's begin. Gonna give us some background, some definitions, so that we know what we're talking about. So we're dealing with second order ODEs. This is a general form for a second order ODE, where f is some given function. If f is linear in y and y prime, we get a second order linear. Which I'm going to start abbreviating it by that because it's too much to write out all the time. So a solar has the form a very important form for you to know. This is the standard form of a second order linear differential equation. Okay. So this is another important form. If you see anything that looks like either one of these, it's a second order linear differential equation. If you cannot write something in this form, not written in this form. Can I name the forms? I might refer to these as numbers. This is form 1. I call this form 2. And I call this form 3. So it's sort of the same idea as the first order linear. You just know this form, and then if it's that, like that, it's linear. And if it's not like that, it's nonlinear, right? Notice again, none of the y's are raised to powers. You don't have two y's multiplying each other. None of that's going on, so that's why it's linear. Another thing we have to define now is homogeneous. It means something completely different from chapter 2, right? Chapter 2 homogeneous means something else. In every other chapter in the book, this is basically what it means. If your g of t or small g, depending on which form you're in, equals 0 for all values of t, homogeneous.
Well,
Yes.
we can divide by what?
You're here
The second one?
Page.
by this p, right? If I want to go in the standard form where the coefficient is 1, just divide through by p. That's what I'm saying. If your p is not 0, we can divide by it to get the standard form.
It's poor grammar.
Hmm? What's poor grammar about?
No.
Anyway, we're in math class. So, did I write down that form? The form P of t y double prime plus Q of t y prime plus R of t y equals 0, which is form 4, is called a homogeneous second order linear differential equation. Right? So everywhere else, it just means that when you put things in standard form, what's on the right side is 0. You call that homogeneous. In chapter 2, it meant something else, but everywhere else, this is what it means. It's just, I don't know why they called it that in chapter 2. It's just that. Otherwise, it is non-homogeneous. Just so you know, you don't call it inhomogeneous when we have bad grammar and stuff like that. That's what it's called. Non-homogeneous. Okay. Yeah, so a lot of notes. So we're going to focus on the homogeneous case for the next 4 sections. In 3.5 and 6. General standard form for a second order linear differential equation, another form for a second order linear differential equation. If the right side is 0, it's called homogeneous. The first 4 sections of chapter 3 deal with homogeneous, but that's actually pretty good because in 3.5 and 3.6 we'll see that knowing how to solve the homogeneous case will actually help us to solve the non-homogeneous case. And so learning how to deal with the homogeneous case first is actually a pretty solid plan. Let's go. We just have to get through this. It's going to be worth it in the end.
So we need to do the homework tonight.
Huh?
We gotta do the homework for this tonight.
Well, if we finish it, that is. Some facts. This shouldn't be very strange to us. We saw that on the first day of class, when I asked you, we had y prime equals y, and I asked you to guess the solution. You guessed e to the x, and then you were like, well, any constant times e to the x should work. And a similar thing will happen here. Meaning, if I know any solution to this equation, then a constant times that solution is also a solution. Right? That's going to be an important fact for us later. The proof is not hard. So suppose you had C1, Y1, double prime. Let's put that Q. Plus R. So this means that the y1 is a solution, right? It means I plug it into the differential equation and it works. It actually gives me 0. Then, if we replace y1 with c1 y1, then this means we get p of c1 y1 double prime, and that is a farad. But
We don't see anything yet.
Oh, God, come on. We're not gonna get through this. Come on, write faster. I got this. I got this. Come on.
Come on, Jhevon.
No.
You can do this.
Come on.
no, we have to go.
Really?
Really?
Are you sure about this? It's just drill over
There's no
here.
fun.
I can't be on camera like teaching you guys.
Turn off the camera! Turn off the camera!